So to talk about problem 7 on problem set 7, there are demos of this on YouTube, and it is hilarious. If you have a circle, and it's upside, we've got cool air now. Downside, the fan sounds like just an air blower, literally. If you've got the circle, let's assume that this is a disc, and what I'm building is, you know those merry-go-rounds on the schoolyard, just those big. I don't know if they do them today because now everything's got to be padded and safe. But back then they had these big steel discs of raw steel that was roughly, let's say the radius of this guy was 2 meters, which is kind of big, but hey, there it goes. And the mass of the disc is 75 kilograms. And this thing can rotate around its center of mass. Basically, there's an axis right there. And you'd go, well, what's the problem? Well, you could actually get a lot of information from just this. You could get its moment of inertia, which is just 1/2 mr squared. So if I simply asked for what's the moment of inertia of the disk, you would just go 1/2 75 2 squared, or 150. Now during normal problems, I wouldn't care much about like the units, but just to let you know, when you give an answer, let's say I asked for, well, what's the moment of inertia of this disk? You need to include the units. And some of you may go, well, how am I supposed to remember what the moment of inertia units are? Well, you just look at the equation. This stuff will be given to you. On the equation page, there will be these things. In fact, if you look at Blackboard, there are sample test 2s that you can look at and look at the equation sheet and what's usually given. When you give a final answer, like an answer that you're going to box, include the units. I am very, very, very picky about units, and I require the graders to do as well. So be sure when you give your final answer that you use the right units. Now, let's say for a moment that we put on this disc 4 children. Now, they're identical quadruplets, so let's just keep the mass simple and identical for all of them. And each child, I don't know, what's the typical mass of a child in kilograms? 40? 30? 30? Sounds about right. Let's make it 30. So 30 kilograms per child. Well, if you put 4 of these children on this disc, how does that change the moment of inertia? Well, the total moment of inertia is the moment of inertia of a disc plus 4 times the moment of inertia of the child. Because you've got 4 of them, each child has its own moment of inertia. They're all at the same distance away from the center. So it's 4 times moment of inertia of a child. The moment of inertia of a child, now granted, I'm going to treat the children like point particles. In physics, you can do that. The approximate shape of a cow, I just treat it as a sphere. And in physics, it's all about approximating stuff So these point children, each moment of inertia is just the mass of the child times r squared. A point particle's moment of inertia is just mr squared. So this becomes 30 times 2 squared. So 30 times 4, or 120. So this becomes 150 plus 4 times 120. And that adds up to be 480 plus 150, 6, oh, I can't do math in my head right now. 630, yeah. For some reason my brain was saying 530 and I was having issues. So that's the total moment of inertia of this disk. Well, I'm going to ask the question, what happens is you get 3 of the children in on the joke, and 1 is not aware of what's going on. All 4 are spinning this disk up, so it takes 2 seconds for it to make 1 revolution. So the period is 2 seconds. Well, if the period is 2 seconds, what can you tell me about this disk? Well, the frequency is this, 1/2 hertz or 0.5. The angular velocity is 2 pi f, which is rather convenient because now the angular velocity is just 3.14 radians per second. And now we need to start talking about something else. In the last week's or Tuesday's lecture, we talked about linear momentum, P, or mv. In the rotational world, we have angular momentum, and it is equal to I omega. So if I wanted to know the moment of or angular momentum of this disk, it's 630 times 3.14 or 633.14. Moment of inertia is kilograms meters squared. Omega is radians per second. Oh, I shouldn't have done that. Hold on, that changes everything. I hit the plus key. $1978.2. Okay. I was looking at that going, I'm not sure. But there we go. So that's the angular momentum of this. Just as like if you had an object moving 3 meters per second and it had a mass of 10, its moment of inertia would be the product of the two in kilograms meters per second. So what these kids do is three of them move towards the center, and if that's the center, then the new distance that these children are from the middle is 0.2 meters. And this child is still out at the edge at 2 meters. Now, what's the point in all of this? You've all seen like figure skating and how the skater has their arms out and they're twirling. And what happens when they take their arms and they move them inwards? What happens? Do they turn faster or slower? They faster. What they're doing is they're manipulating their moment of inertia. They're taking advantage of it. Because just as there is conservation of linear momentum, there is angular momentum. Is conserved. Angular momentum is conserved. The law of the conservation of angular momentum is that L initial is equal to L final. So these moments of inertia at the beginning here, it's 1978.2. Here, the angular momentum will also be 1978.2. So L final is 1978.2 kilograms meters squared second. Well, let's see what happens. The first thing you really need to do when doing a problem like this is that now that you understand what it looks like after the change, is to calculate the moment of inertia after the change. So the new moment of inertia is the moment of inertia of the disk plus the moment of inertia of one of the children plus 3 times the new moment of inertia of the child. Because you've got 3 at the inner radius and 1 at the outer. So the moment of inertia of the disk doesn't change. So it's whatever that number is. The moment of inertia of that first child doesn't change either. So this will be 150. This will be 120. And then 3 mass of the child, new R squared. So 3 times 30 times 0.2 squared. And that will give you $273. Oh no, hold on. Yeah. Okay. 273.6. Now that I've done, after I made the error with this, now I don't trust anything I think of. So the new moment of inertia is roughly half of its original moment of inertia. Well, angular momentum conservation says that the angular momentums have to be the same. Angular momentum means I initial omega initial is equal to I final omega final. I initial over this is omega final. That the final angular velocity can be learned from this, which is now, let's see, 630 times 3.14 divided by 273.6 . And I get 7.23 radians per second. So this thing was initially turning at the rate of 3.14 radians per second. Now it's turning at the rate of 7.23 radians per second. Well, what's the new frequency? What's the new period? 2 pi f final is equal to omega final. So final frequency is omega f divided by 2 pi. So 7.23 divided by 2 pi. .15 hertz. The initial frequency was half a hertz. The new frequency is 1.15 hertz. In this case, the period, the new period, is now 0.87 seconds. So instead of making one turn every 2 seconds, it's now making a rotation every roughly 9/10 of a second. So this thing spun up. Now, what's the fun part in this? Well, if you're aware that you're going to do this, but your buddy isn't, 3 of you move towards the center, the frequency basically doubles. The radial acceleration initially is v squared over r, and v is omega r. So this becomes omega squared r squared over r. And we've seen this before, that the radial acceleration is omega squared r. Initially, the child who was at the edge, and one of the things that I would do, I really need to sit down and come up with some reasonable numbers. But the initial radial acceleration was 19.7 meters per second squared. Now, to get something where the radial acceleration is 19.7 meters per second squared, that's roughly 2 G's of acceleration. So it's basically twice that of gravity. Now, if you were experiencing an acceleration of 20 meters per second, if all you had to do was just hold on with dear life, 2 G's isn't that bad. I mean, you're gonna feel it, you're gonna stretch out, and a lot of people would probably just fall off at that particular moment. But you could probably do it. The new radial acceleration is 7.23 radians per second times 2. Now, what I'm going to do is, well, yeah. So for the children that have moved towards the center, and these kids probably are going to fly off anyway. Oh no, it's not that bad. For the kids who move towards the center of the circle, their acceleration actually went down to 1g. Totally legitimate. They could stay on that thing, not too bad. Let's talk about the poor dude in the middle, or the poor dude at the edge. His acceleration is 104.5 meters per second. Roughly 10 Gs. So it goes from 2 Gs to 10. Basically, that kid is flying off. Would be ripped off. For normal humans, will start to black out at about 6-7 Gs, 60 to 70 meters per second. The blood just rushes out of their head. At 10 Gs, they're going to get flung off. Typically, it's not, I think the ones on a normal school ground, you could probably get up to 3 or 4 Gs, and then you get flung off. 10 is a little bit unrealistic. But it does demonstrate the idea of, if you were at a playground and you've got one of these things, I've actually attempted it myself, where if you get that thing rotating and then walk towards the middle of the disc, that disc will start spinning up. So if you're unprepared for that acceleration, it could take you by surprise, and then you get flung off. So it is, you can have a little bit of fun to your unsuspecting friends by doing this. It won't get that high, but it'll get high enough where they feel it. And so this illustrates the conservation of angular momentum. You can do the same thing if, like, if you had a record and you had just a spinning disc, and good frequency for back in the day when they put music on discs. 33 1/3 rotations per minute would end up being let's see, per minute, so 1 minute 60 seconds, so that 33.3 divided by 60 is 0.555 hertz. So the record is spinning at 0.55 hertz, and you drop a record on top of that disc and they stick. So again, we have conservation of angular momentum. The record is initially at rest. Spinning disc has a frequency of 0.55 hertz. So once again, the angular momentums are conserved. Initially, the only thing that's moving is the spinning disc. The mass of the record is 1 kilogram. The mass of the disc is 5 kilograms. So moment of inertia initially is I initial omega initial. This is I final omega final. 2 pi f is equal to omega. So we can substitute in that. 2 pi's canceled. And the initial moment of inertia divided by the final moment of inertia is the final frequency. So really what I'm doing, over here I did it numerically and showed you all the little bits and pieces. Now what I'm really going to show you is if I asked for what is its final frequency, this is how you would do it. And interestingly enough, it looks a lot like problem 8. So our initial frequency is Fi. The initial moment of inertia, the only thing that's moving is the disk itself. So it is 1/2 mass of the disk r squared. And the new moment of inertia is 1/2 mass of the disk plus mass of the record r squared. Because the disk and the record have the same radius, I'll just say r. Now, one of the things that people tend to freak out on is, first question, did I give you the radius of the disk or the record player? No. Next question, do I need to give you that value? No. Why not? The r's cancel. The 1/2's cancel. So in one of the things that I do, I understand you guys love to have your plug and chug, but there are little things that I can do to interrupt that. One of the things is I understand how the problems work, and in certain situations I may not give you the mass because you don't need it, because it just cancels out. And then you can see that this is all equal to Fi, mass of the disk divided by mass of the disk plus mass of the record. So this becomes 0.555 mass of the disk. Actually, I got these flopped around. Oh no, I don't. No, I'm right. And the new frequency is 0.4625 hertz. So the frequency does change a little bit. It would slow down, which kind of makes sense, because if a big mass that's moving hits a small mass that's at rest and they stick, it'll keep moving but not as fast. Kind of like I don't know, like just a big lab just slamming into a chihuahua on a smooth floor. They'll keep moving, but not as initially as fast as the dog was to begin with. So this illustrates conservation of angular momentum, and that rotation frequency is based upon its mass distribution. You can take advantage of all sorts of things by understanding its mass distribution. Yes. What's this? 0.4625. Yeah, it's curving just a little bit. Hold on. Whew. Okay. Now, one of the things, really, I believe that's kind of everything that we need to talk about in terms of new material. That test 2, you're going to have the normal appetizer and 3 problems. The appetizer will be the right-hand rule game. What generally happens with this is if the class just chews it up and gets that 5 points immediately, and I see as the class that we've mastered that technique, it won't show up on the final. But if it tends to be a big problem, then we put it back on the test, or back on the final. The other 3 Atwood's machine with energy, Dr. Eschenberg's rule on Atwood's machine and tests. Every test in 213 will have an Atwood's machine problem on it until we all master it, which means it will be on 213 tests and finals forever. But in this particular case, we're going to use energy and not motion. In the problem set that's due today, you're basically looking at all the old problems on inclined planes and Atwood's machines, and I'll touch on that in just a second, and using energy with that. 2, torque bar. Basically similar to the last 4 problems on problem set 7. Very similar to what you guys did in lab this week. And then, torque was this week. And then there would be, I haven't figured out what, it tends to be a wild card. Collisions or rotation. I haven't figured out which. If it is rotation, it'll either be angular acceleration is equal to 0, or angular acceleration is not equal to 0. The big 2 classifications or problem classifications break down into either A, fish of fury, or the disc with the force at the edge, similar to some of the problems that you saw on problem set 5. And so that's really the test. Standard 25 multiple choice. We meet here a week from today to take it. And sample test 2s are out. The test 2 bank is out. What I'll do over the next couple of days, I'll work through the multiple choice so that you guys can look at it. Before I continue on with the other stuff, we've got the tutorial tomorrow at 1. I think in here. Well, Tuesday will be a review lecture, and then I want to say on Wednesday I've got a room for the test 2 review, so we'll take a look at that. Now for Energy and Atwood's machines, which it will be on the test, the one that you need to pay close attention to is, I believe it is problem 8 from problem set 4. No, not 4. 3, I think, maybe. Where you've got one mass on a flat surface, the other mass hanging. It's going to be similar to this. There is friction. Boo, friction. And this has a particular height, which we'll call L. At the end of the motion, oop, not you. It's moving with a particular final velocity. The initial velocity will be 0 and has just overcome static friction. The question will be, given this situation and given an assortment of conditions, determine the missing condition. Now really what I'm trying to do with this is I'm going to give you a general solution. If you can remember this general solution, you can be ready for anything that I throw at you when it comes to this problem on the test. Right now, you're going to have to take that little part of your brain that is sitting there screaming at you going, he hasn't given us any numbers, except for those little numbers. And then accept the fact that physics is about manipulating equations, not about manipulating numbers. That's accounting. Here, we have an initial energy. Here, we have a final energy. Now, there is friction boo, friction. So we know that the energy that's initially there minus the work removed through friction is equal to the final energy. Here, it's at rest, or the system has just overcome static friction. So what is the value of the kinetic energy at the beginning? Should be 0, yes. So there is no kinetic energy. The key with solving these types of problems is setting up the conditions, identifying and putting together the conditions at the beginning and at the end. At the beginning of the motion, it's not moving, so you know kinetic energy is 0. Now this particular block here, block 1, does it change its potential energy? No, it remains at the same level. So the only thing that can contribute potential energy to the system is mass 2. The potential energy initially is M2GH. That's the potential energy of the system. the energy at the final, this has just made contact with, or it's the instant before contact with the ground. Remember, the snark rule or the Meg rule is in effect. So if you go, the velocity of M2 is 0 because it hit the ground, ha ha ha, I'll be like, what an odd coincidence. Your grade is 0 as well, ha 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 ha. So remember, it's the moment before impact. L is the length, the distance from there to there.
Yeah, no. So potential energy is the L.
Oh, yes, thank you. I have to be consistent with my... The energy final, there is no potential energy. This block can't move up or down. That one is at the bottom. So it has no potential energy. So there is none. The kinetic energy final is equal to 1/2 m1 v squared plus 1/2 m2 v squared. Or I could simply write 1/2 m1 plus m2 v squared. Why do I not make any or note any difference between the two masses, velocities? Because they move as one. If they had different velocities, the string would snap or it would bunch up, which doesn't make any sense. So the velocities have to move as one. Now we've got this work thing over here. It's basically a block that's being pulled, mg down, normal force up, mu sub k to the left, the tension to the right. But all I'm interested in is the energy removed by friction. Work is the friction force times the distance. What is the value of the distance that block 1 has moved? L. Because if block 2 drops L meters, block 1 will shift L meters as well. So this becomes that. Friction force is mu sub k times normal force. So this becomes mu sub k, normal force, L. Now what's normal force? Well, you could probably in a test get away with just saying sum of the forces in y is 0. In the test, we've got a lot of complex things going on. This is as complex as I want this to get. I'm not going to put any weird angles on this. Everything will be perpendicular. My dream eventually will be to teach Honors 213, and oh my goodness, the fun we're going to have in there. So this becomes that normal force is equal to mg. So this becomes mu sub k mg L. And actually, real quick, which M am I talking about here? M1 or M2? M1. So remember, to label your masses, because if you lose the labeling of your masses, things can go bad quickly. So there we go. Now let's put the pieces together. The energy initial, M2GL. The energy removed by friction, mu sub K, M1GL, equal to 1/2 M1 plus M2 V squared. So let this right here, what's really interesting is when I first started teaching one particular summer, I taught physical science. And I asked one of the professors, what do I do? I've never taught physical science before. And he's like, you give them the problems. Just tell them. I'm like, but then they'll get 100% on the test. And he goes, no, they won't. They won't believe you. So what I've kind of done is I've adapted it to pre-med. You get a lot of the multiple choice. I give those to you. I'll change a few things up. But for the problems, I'm more interested in you understanding the problem-solving technique. This is the core of Atwood's machine. In all the different cases that you have, be able to derive it from there to this equation right here. I'm telling you now, it's no secret. So what are the things that I could do? I could play a conventional solution. I could say, well, with mu sub K equals 0.1 and M1 equals 2 and M2 equals 20, L is equal to 10, G is obviously 10. What is the final velocity? Well, if you've got this equation right here, the first thing that you could do is you could obviously solve for V. You, in fact, could solve for any of the variables. If you could take this equation, it's a lot like you now understand how to fish. Because no matter what I'm telling you to do, you could just factor stuff out and solve for it. So this becomes 2 M2GL minus mu sub K M1GL divided by M1 plus M2, and that is equal to V squared. Take a square root. I'm going to factor out a G and an L. So V becomes the square root of 2GL M2 minus mu sub K M1 over M1 plus M2. And so there you go. So this becomes 2 times 10 times 10, 20 minus 0.1 times 2 plus 20, and this becomes 13.4 meters per second. That would be something that we could do. Now, one of the things that I do in 213 is I basically know that you guys are plug and chuggers. So what I did on one particular occasion, I've done it on several occasions in different ways. But let's say I did this. Mu sub k is 0.1. L is still 10. We're still on the Earth. But now I'm going to say that M2 is 10 times the mass of M1. Is that it? Yeah, that's it. When I did this on a test, people lost their ever-loving minds. And they all said the same thing. You didn't give us the mass. And I go, I know. It's a correctly constructed problem. And then I cackled a little bit. And later they said it was impossible. It would take too long to do this. And I'm like, oh, really? And so I started with this equation. And I said, but I gave you that. So this is 10m1 GL minus mu sub k m1 GL is equal to 1/2 m1 plus 10m1 v squared. Factoring stuff out, m1 GL 10 minus mu sub k equals 11 m1 over 2 v squared. In an Atwood's machine problem, you don't need the specific masses if you have the ratio of the masses. The masses go away. And then you're left with 2 over 11 GL 10 minus mu sub k is equal to v squared. Square root 2 over 11 GL 10 minus mu sub k which then becomes 2/11 or 2/11 10 10 10 minus 0.1, and this becomes, and I just want to confirm it because I know what the answer is already. .4 meters per second. Because all I did was, if M2 is 20 and M1 is 2, then M2 is 10 times M1. I just looked at the ratio and just plotted it out. So, once again, I keep doing this over and over again just so that you guys know. Sometimes I give you numbers that you need. Sometimes I don't give you numbers because you don't need them, as this example. And then other times, I give you numbers that you don't need and I just watch while you try to cram a square peg into a round hole and wonder why you can't use, why you can't use it, because sometimes I give you information it's just unnecessary. As an example, if it's 4 o'clock in the afternoon, given this, what's the final velocity? The time of day doesn't matter. But anybody who tries to plug in 4 p.m. into the equation, then I know you don't really know what you're talking about. Another thing that could be done is, given a set of conditions, find mu sub k. You should be able to take this equation and solve for any variable in the equation. So if I needed mu sub k, m2gl minus 1/2 m1 plus m2 v squared equals mu sub k m1gl. And there you go. Likewise, you should be able to solve for L, for G, for M1 or M2, any of that stuff. So it's in, what's really funny is I'll read it. I'm thinking about just posting it on YouTube. You have celebrities reading hateful tweets about them. I have the most hateful review of my class and me personally ever. And one of her main complaints was all Physics 213 is applied algebra. Yes, it's exactly what it is. So there's nothing that I'm really, it's taking your last algebra course. We could consider this course like Algebra 3 or however algebras you got to take. But it's the second part or third part or whatever. You should be able to do all of this stuff and manipulate the letters. Equation manipulation is at the core of what it takes to do physics. So what I'll do tomorrow is I'll go over some problem sets. To those of you who think we're about to leave in the next minute, you're right. It's long. It's been a long day. So let's just end it. All right. If you got any questions, office hours are coming up, and I'll see you tomorrow at 1.